Okay, hello. Oh, it's up. All right. Hello, everybody. Um, so I don't know why it's not appearing here, but whatever. Uh, I'm gonna just quickly check. Okay, 6. Okay, it's up. All right, it's up. Hello, everybody. Welcome to MathSoc's 2501 and 2601 linear algebra seminar. My name is Cyril. I'll be the only one presenting this part, for Martin and Oscar have sadly departed from us. So I guess this is not applicable because this is an online thing. But this is the content we'll cover. We'll cover eigenvalues, eigenvectors, then we'll move on to canonical Jordan form, and then matrix exponential. This last chapter will be very small, so should be good. Cool. Hopefully, sound and everything is good. I'm gonna open this tab here and mute it. Okay, and I'm gonna keep the chat there. All right. If you have any questions, just ask in chat. Will this be uploaded? Yep. Yeah, you can see the previous one, the previous recording. After this live stream is done. Okay, cool. Let's say we have a vector space. Let's start with the definition of an eigenvalue and an eigenvector. So basically, when you apply your linear map T onto a vector V, right, and you get a scalar multiple of that vector, then we say lambda is an eigenvalue, and we say V is an eigenvector. And we say specifically V is the eigenvector of that eigenvalue lambda. And not all eigenvalues are attainable. Specifically, the set of eigenvalues which are attainable is called the spectrum. Before we go into defining some properties of eigenvalues and eigenvectors, it would be good to define this notion called T invariance. So T invariance refers to when you apply. Let me go down here. So T invariance refers to when, if you apply T to like every set of vectors in U, then you get some subset of U. So like you can imagine you have some set U. If you have like all the vectors mapping to like vectors inside U, right? Like it can be the entire space U or it can be like some subset of it, then we say U is T invariant. So it's like preserving itself. And yeah, so this is going to be nice to define one of the properties. So this is the normal definition of eigenvalues, eigenvectors. We also say that for eigenvalue lambda, its eigenspace is denoted E of subspace lambda, and the eigenspace refers to the vector space of all of its corresponding eigenvectors. So formally, we write this as the kernel of T minus lambda I. If you're wondering where this comes from, essentially, it sort of comes from the idea that if you have TV equal to lambda v, right, then you can write this lambda v as like the identity function or matrix. Let me write this out clearly. Lambda times like I times v, and you can rearrange your equation, right? So you get T minus lambda I, and v gets mapped to 0. So v is in the kernel of that matrix or map. Eigenspaces are T invariant, if you remember how we defined it. That is, if v is an eigenvector, T of v is also an eigenvector. And eigenvectors of different eigenvalues are linearly independent. So a consequence of this is that eigenspaces of different eigenvalues are disjoint. So we get this property. This means you can actually direct sum them. And a matrix A on Fn is a square matrix A on Fn is diagonalizable if and only if there are n linearly independent eigenvectors. So that is to say, if you can have a set of eigenvectors which span the entire space f of n, then this matrix is diagonalizable. There's some other ways of writing this property. For example, like the degrees of the eigenvalue or eigenspaces will add to n, or the direct sum of the eigenspaces will be f of n. We'll see all of these notions. Cool. So let's define this thingo. We call the characteristic polynomial the expansion of the determinant of a minus lambda I. So notice a is constant and I is obviously the identity matrix that's constant. Lambda is going to be your parameter. So the characteristic polynomial is a function of lambda. And we also define algebraic multiplicity, and geometric multiplicity. So algebraic multiplicity is going to be the multiplicity of each of the roots of a minus lambda I, and geometric multiplicity is going to be the dimension of the eigenspace. So let's just give an example. Let's say you do your a minus lambda I and you calculate its determinant to get the characteristic polynomial, and let's say you get 3 minus lambda times 2 minus lambda, all of that squared. So this is your characteristic polynomial. Your eigenvalues are your roots, so that's 3 and 2. And we say 2 has an algebraic multiplicity of 2 because, its factor is raised to the power of 2. And we say 3 has an algebraic multiplicity of 1 because it's raised to the power of 1. However, note that the geometric multiplicity is different from the algebraic multiplicity. The geometric multiplicity is the dimension of the eigenspace. It'll always be less than the algebraic multiplicity, but we aren't guaranteed it's equal to. Less than or equal to, but we aren't guaranteed it's equal to. So as an example, the geometric multiplicity of 2 could be equal to 1. So it's possible gm2 equals 1. It's also possible gm2 equals 2. But note there are no other values because the geometric multiplicity must be at least 1. This is an important property. We'll show what this implies when we're doing like exam questions. So matrix A is diagonalizable if and only if for every eigenvalue lambda I, we have gm lambda I equal to am lambda I. So have a think about why this is the case. Firstly, you must have that the sum of your multiplicities is equal to n, right, for each of the eigenvalues. So another way to say that is that the sum of am is equal to n. You must also have, that's about it. So you have the sum of am equals n, and if each of the geometric multiplicities is less than or equal to am, right, the only way you get this property here, where you have n linearly independent eigenvectors spanning, is if the geometric multiplicity equals the algebraic multiplicity, because only then can you add up all of your eigenspaces and make them equal to n. So you can also keep that in mind. And this is the worded explanation here. So let's use all of our knowledge to find the eigenvalues, eigenvectors, and then find the algebraic and geometric multiplicities. So for the first one, we'll show that we'll use the determinant and trace method. So for this first matrix here, we can calculate its trace and its determinant. So the trace is calculated, the trace of this matrix, so let's say the trace of A is going to be the sum of the diagonal entries. So 1 plus 4, right? And it just so happens that the sum of the diagonal entries, the trace, is also equal to the sum of eigenvalues. It turns out that the determinant of A, right, which is you calculated by taking your normal determinant formula, so 1 times 4 minus 2 times negative 1, so 4 plus 2, that's 6. So this is your trace and this is your determinant. The eigenvalues sum to this, to the trace. The eigenvalues multiply to the determinant. So we get that over here, so we can inspect and find the eigenvalues. So first, importantly, note that the algebraic multiplicities of these two are 1, right? And secondly, note that because the geometric multiplicity must be less than the algebraic multiplicity, but it must be at least 1, the geometric multiplicity actually must be equal to 1, because you can't go higher than 1, and you can't go lower than 1, therefore you must be at 1. So we found like our eigenvalues and the geometric and algebraic multiplicities. I've also listed their eigenvectors here. I haven't shown how to calculate them. I'll show that in a different example. But this is how you calculate eigenvalues and eigenvectors. Cool. So this is not, for the second question, this is not the only way to calculate the eigenvalues. And this only works for 2x2 matrices. For 3x3 matrices or more, you have to use the, if you remember earlier, the formal definition of the space of, you have to use the characteristic polynomial. So that's determinant of A minus lambda I. Right, so that, and after doing this, right, so in this case we use T instead of lambda, this is fine. You expand the determinant, so you can either expand over the row or the column, standard determinant calculation. So let's say we expand over the row. This is going to be positive, negative, positive. This is your only non-zero term. All of these here are 0, so they don't count to the calculation. So you take 2 minus t times the determinant of this submatrix, right? And the determinant of this submatrix here is 3 minus t squared minus 1 squared. And then you can use difference of squares to factorize this. So you get 3 minus t minus 1 and 3 minus t plus 1, which gives you this expansion over here. And then you just multiply this back in. So you can see 2 has an algebraic multiplicity of 2, and 4 has an algebraic multiplicity of 1, because 2 minus t is multiplied twice. Cool. So now we want to sort of find their eigenvectors, and I'll show you, since we didn't show it here, I'll show you this now. We use the formal definition of the eigenspace, which is that the space of eigenvectors is equal to the kernel of A minus lambda I for the eigenvalue lambda. So what we can do is we subtract lambda I from this matrix here. So for the eigenvalue of 2, we subtract 2 from each of its, sorry, not here. We subtract 2 from each of the diagonal entries here, here, and here. So we end up with this matrix here. And then to find the kernel of this, you row reduce. So this matrix here will get row reduced to zeros on the first 2 rows, and then 2 1s in this column. And then you can solve for when this is equal to 0, like this. So your augmented matrix calculation looks like that. So note 1 that there's only one linearly independent vector in your rows, which means that the kernel has a dimension of 2, so the nullity is 2. So then you find your eigenvectors by how you did it in your first year, how you found the kernel vectors in your first year. So that would just be solving. There's 2 solutions. You either set 1 here and 0 here, so that'll give you like 0 adding everything, or 1 and negative 1 here, so that can see 1 minus 1. Then you do the second matrix for the eigenvalue of 4. You get this. Notice that one of these rows row reduces to zeros, and then you find the remaining eigenvector. So we can see that we have 2 linearly independent eigenvectors here for eigenvalue 2. This means that the geometric multiplicity for 2 is 2. And remember that the same logic as before, geometric multiplicity has to be less than or equal to algebraic multiplicity, which means that for 4, it must be 1, because the algebraic multiplicity is 1, and it has to be at least 1. But you can also see here the dimension is 1. Cool. Right, so this time we're asked in this question to find all eigenvalues, so not just the ones we're given, for example, and also calculate the algebraic and geometric multiplicities. So this is where the AM less than or equal to GM property comes into be useful. So for this matrix C here, we're given 2 and -3 are eigenvalues. Whenever you see like one missing eigenvalue, you should immediately think trace, right? If you see two missing eigenvalues, then you should think to use the trace and the determinant, right? So one missing eigenvalue, just use the trace, and then 2, you use the determinant. And then for this one, we're given the eigenvectors. We'll see how to do that one. So for this one, we're given the eigenvalues. The trace is the sum of the diagonal entries. So in this case, it's 3. Yep, 3. And we subtract off these eigenvalues here. So we subtract off 2 and subtract off -3. So, we get 2 plus 8 minus 7, that's 3. We have eigenvalues 2 plus -3, which equals -1. So the remaining one must be 4. So that the sum of eigenvalues is the trace, which is 3. So notice that we get 3 distinct eigenvalues, 2, -3, and 1. Sorry, 4. 2, -3, and 4. Those are our eigenvalues. It's important to note that each eigenspace must be non-zero, right, for each of these. This means that the algebraic multiplicity must be at least 1. However, note that this is a 3 by 3 matrix. Also remember, your eigenspaces, right, the sum of the dimensions of your eigenspaces must be less than or equal to the dimension you're working in. So right now we're working in, say, R3. Okay, so the sum of the algebraic multiplicities can't be more than R3 because the eigenspaces are like linearly independent from each other, like the corresponding eigenvectors in different eigenspaces. So you must have the algebraic multiplicities evenly distributed as 1, 1, 1 to each of these eigenvalues. There's no other way to do this. You can't have 4 have like an algebraic multiplicity of 2. Similarly, this means the geometric multiplicity must be 1, again by that same reasoning from all the way before. The geometric multiplicity is less than or equal to the algebraic multiplicity, and is at least 1. The only possible value in this case is 1. So we get the geometric multiplicity and algebraic multiplicity is 1. Cool. Now, in this case, we're given a matrix and we're given 2 eigenvectors. So no need to think too complicated on this one. All this question really needs us to do is just find the eigenvalues for these 2 eigenvectors. So I won't do the calculations here, but if you apply if you do your normal matrix vector product and do D times this vector here, you'll get 3 times that vector. And if you do this vector here, right, you'll get 1 times that vector, so you'll get its vector itself. So you found your 2 eigenvalues are 3 and 1, right? And then you use the same trace calculation from before. So the sum of the diagonal entries is 8, and the sum of the eigenvalues is 3 plus 1 plus a third eigenvalue. That third eigenvalue must be 4 as such. And then by exactly the same reasoning here, the sum of the algebraic multiplicities must be less than or equal to the dimension of R3, right? And that must mean the algebraic multiplicities are all evenly distributed to 1 because there's no more space to fit. Geometric multiplicities are less than or equal to, or at least 1, and at least 1. So everything is 1. All multiplicities are 1, algebraic or geometric. All right. Cool. All right. So let's talk about diagonalization. So we described this briefly as having n linearly independent eigenvectors. So you can diagonalize if and only if you have n linearly independent eigenvectors. But again, as was also mentioned, we can express this in different ways. So we talked about these two ways, right? You can have the eigenspaces, when directly summed together, fully span what your linear map works in. And we also have the sum of the geometric multiplicities, which actually refer to the dimensions of these eigenspaces. They all add up to the dimension of V. So these are 3 and 4 are clearly analogous, and that's analogous to the n linearly independent eigenvectors thing. And having n linearly independent eigenvectors, because eigenvectors are all, linearly independent, like for different eigenspaces and, within the eigenspaces, then, having n of them means that you have a basis. So yeah, it's just a lead up from like the previous result. All right, so to use this, we say let V be a vector space, and we define a basis here. And we define our some rules on each of these basis vectors. And we ask, is there a basis B for V such that the matrix T with respect to B is diagonal? And it wants us to explain. Okay, so T being diagonalizable means that V means either any of these three properties. The lead up from 2 is that V is the, one important one is like V is the direct sum of eigenspaces, or, analogously the sum of, the dimension is the sum of geometric multiplicities. So if we can find T in this particular basis V here, right? So if we find the matrix for this particular basis, and then try and find its eigenvectors and eigenvalues, right? We can check if the geometric multiplicities add up, right? So if we can do that, that means that, our eigenvectors might change, but the dimensions of the eigenspaces will never change for different bases. So we can just use this particular basis here. So the way we would do this is like, we note these rules, and we kind of say like, we define like a vector B as being like the coordinate vector on the basis B. So like if we have something like 1, 2, 2, this represents having like one combination of vector 1, two combinations of vector 2, and two combinations of vector 3. So we write the matrix with respect to B, right? So this part here is TB as such. Notice how the multiplication factors out. You take 2 of, so for the first result, you get 2 of A. For the second result, you get 1 of A, 2 of B, 1 of C. And for the third row, you get 1 of A and 1 of C. So if you're wondering how all of this corresponds, the column vectors represent each of these corresponding calculations. Because upon expanding this out, what you get is, like if you expand this out, so let me do this, this becomes A times 211 plus B times 020 plus C times 011. Right? And each of these sort of corresponds to like each of these rules over here. Cool. Then what we do, and I should also say, when you like sum all of these up, each of these, the results will like individually represents like the coefficients in front of V1, V2, and V3. Cool. Now, if we take this, the characteristic polynomial of this, do the determinant calculation. So you subtract lambda from all of these, you expand over the row, and then you find the determinant of this submatrix. You can find the characteristic polynomial, and you find that these are your eigenvalues. So let me take off all this. Yeah, so these are your eigenvalues, and so now you want to like check its geometric multiplicities. So you use the kernel method. That's how you find the dimensions of eigenspaces. So first you note that the geometric multiplicity of 1 will always be 1 because its algebraic multiplicity is 1. And then we only need to check the geometric multiplicity of 2 because it could be 1 or 2 because the algebraic multiplicity is 2. So we check the dimension of this kernel, we expand and row reduce, noting that we can't actually row reduce any further, or any further past this. So you get 2 non-zero vectors in the rows, which means that the dimension of the kernel is 1, right? The nullity is 1. So that means the geometric multiplicity is less than the algebraic multiplicity in this case. So it doesn't actually span it, because 1 plus 1 is less than 3. Go figure. Cool. Yeah, so we say T cannot be diagonalized because this basis here shows us the eigenvalues, and it shows us the eigenspaces, eigenvalues and dimensions of the eigenspaces, and it shows us we can't diagonalize it. Cool. So this is mostly 2601 content, but there's a special case of this theorem Math2501 students need to know, so worth listening in on. Firstly, we define what this notion of a normal matrix, or a normal map. So we say it's normal if it commutes with its adjoint. So T composed T star is equal to T star composed T, and an analogous statement for the matrix. Note that the adjoint, as a reminder, is the transpose, and if it's a complex matrix, you take the conjugate of all of its entries. So here's some cool properties of normal matrices. If T is normal, then applying T to V and getting its magnitude will be equal to applying the adjoint of T to V and getting its magnitude. These are all proved in the lectures, by the way. If T is normal, then subtracting a scalar multiple of the identity is also normal. The eigenspace of T is the same as the eigenspace of T adjoint, where the first one is associated with lambda and the second one is associated with lambda conjugate. And also, finally, if T is normal, the two eigenspaces corresponding to distinct eigenvalues are orthogonal to each other. So this one's kind of interesting. This is like saying, if you have an eigenspace that looks like this, and an eigenspace looks like this, if they're normal, they will be orthogonal to each other. And it turns out this is actually almost an if and only if. You also need to go the other directions, you need your eigenspaces to fully span the dimension of the vector space you're working in, and if they're orthogonal to each other, then they are normal. Okay. So let's say we have A being a normal matrix. The eigenvectors corresponding to distinct eigenvalues are orthogonal, right? So we saw this earlier. This is called the spectral theorem for normal matrices. And there exists a unitary matrix Q such that Q inverse AQ is equal to QT AQ. So this is kind of what we were talking about earlier. The fact that because this orthogonality thing means that you will have a unitary matrix Q, which is like your matrix of eigenvectors for diagonalization. So your matrix of vectors for Q, they'll all be orthogonal to each other. So this represents the fact that you have eigenspaces all at orthogonal to each other. So right angles, or in the complex case, just orthogonal. So here are some examples of normal matrices. One is a Hermitian matrix. So the real version of this is a symmetric matrix. Just as a recap, Hermitian matrix is such that A star is equal to A. And apart from getting the properties of normal matrices, we also get that all the eigenvalues are real. And we also have a unitary matrix. So regarding this, a unitary matrix is such that A star is equal to A inverse. And what you get here is that all the eigenvalues lie on the unit circle, right? So this one, all the eigenvalues are real. This one, all the eigenvalues lie in a unit circle. Cool. And it's also worth mentioning, like, nice thing about normal matrices is that they can always be diagonalized. This is what the spectral theorem here says, but it's like you can, if you're given a matrix as normal, you can immediately go, yes, I can diagonalize that. Its geometric multiplicities all add to the dimension of the space. Cool. So let's use these results in some questions, if we can remember them. So you're given this matrix P here, and bing, ding, 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 we're given that it's orthogonal. Aha. So we can immediately say a lot of things about this. It's going to be very useful, these results. So firstly, we say P being orthogonal means that it's diagonalizable, which means that its algebraic multiplicities are going to be equal to its geometric multiplicities. But also being orthogonal has like a bunch of properties. So firstly, let's start with this. We want to show that the kernel of P minus I is spanned by these two vectors. You can assume, you can like sort of infer this is basically saying, because this is the form of the eigenvectors, right? This is the form of like the eigenvector definition. This doesn't imply that this is an eigenspace, the way it's written out. It's sort of, but you can sort of assume that it's trying to ask you to show that these two vectors here are eigenvectors with eigenvalue 1. But anyway, you want to show that this kernel here is spanned by these eigenvectors, and it also wants you to explain why the spectrum of P is 1, 1, I, and negative I. Notice also, like, notice that all of these have magnitude 1. I wonder if that's important in any way. Okay, so you're given kernel of P minus I. Row reducing, it gives us that, these two rows here are all zeros, and you have two non-zero rows here. So this means that the dimension of the kernel is 2, so because 4 minus 2. So the nullity is 2, and you know that these are all linearly independent to each other, and so you know this forms a basis for the kernel of P minus I. Cool. Yeah. All right. I think so. Another option. So right here. Like another option is to like multiply P by each of these vectors, and find that they're eigenvectors, and conclude that they both have eigenvalues 1, and also that they lie in the kernel of P minus I, right? So, yeah. So I mean, it's not mentioned here, but you can do a calculation here, which basically goes like P times each of these vectors 1, 0, 0, 1 is equal to 1, 0, 0, 1. So that's another way to solve part I, but that also allows you to say that there are two eigenvectors which span the kernel. Cool. Okay, yeah, sure. Yeah, so this calculation here allows you to show like these are the only vectors which span the kernel. So that means that the geometric multiplicity of 1 is going to be 2, right? But this also means that from the spectral theorem, the algebraic multiplicity of 1 is 2. Sorry, not from the spectral theorem. We know the algebraic multiplicity is also 2, because again, for a normal matrix, the direct sum of all your eigenspaces will be equal to 4, which is the dimension of where the matrix operates in. So that allows you to conclude the algebraic multiplicities, what the algebraic multiplicity is. So you also know that because it's a, let's see, because it's a unitary matrix, right? Which is like the real version, so which is the complex version of orthogonal. All of its eigenvalues must lie on the unit circle. So this means that the trace of p is equal to 2, right? So there's a couple of ways you can go from this. So if you know its eigenvalues lie on the unit circle, but all of these entries are real, the trace is real. We have 2 real eigenvalues, so the 2 eigenvalues must be conjugates of each other, or alternatively, you find the traces directly equal to 2. 2 of the eigenvalues are 1, and so your 2 remaining eigenvalues must be I and negative I. Nice. You can actually also just work with 1, 0, 0, 1 and 1, 4, 0, negative 1. So from before, show directly their eigenvectors, show they're linearly independent, so you solve part I. And then you can like sort of try and solve part double I by finding these 2 eigenvalues and then going back here and concluding the geometric multiplicity must be 2. But all of this is fine. This is also a good way to do it. Cool. So, we're going to introduce the notion of a rotation matrix. So a rotation matrix is, for the 2D case, is in this form, right? So this is always going to describe a rotation. For 3D matrices, you can have rotations and reflections composed on top of each other, or sometimes just rotations. So we have like the 3x3 orthogonal matrix, right? So it has an orthonormal basis for R cubed. We say that an orthogonal matrix is either going to be a rotation or a reflection composed with a rotation. So I'll just highlight that. And these are the only 2 forms it can take for, again, a 3x3 real matrix. So Q, if this is the case, then Q is going to be unitarily similar to either this one, or it's going to be unitarily similar to this one. So the way you distinguish these 2 matrices, note that these 2 submatrices here are exactly the same. You distinguish them by this 1, negative 1 here, right? But, you know, trying to find if it's unitarily similar isn't immediately clear. Like, it's not immediately clear how to do this, but one really easy way to check is by just calculating the determinant. So, you know, if you calculate the determinant of this submatrix, you notice that it's going to be cosine squared alpha plus sine squared alpha, which is equal to 1. So the only determining factor for the determinant is going to be the top left entry, which is 1 or negative 1. So here the determinant is 1, here the determinant is negative 1. And that's how you determine if it's a rotation or a reflection and a rotation. So yep, here's that theorem over here. So if the determinant is 1, it's a rotation. If the determinant is negative 1, it's a reflection and rotation. And we can also determine the angle of rotation by using the trace. And we can also calculate its axes. So we'll see how to do that. So this question here wants us to give a geometric description of this matrix. First, we want to check its orthogonal. That's kind of what it's like hinting us towards, but if we do that, we notice the dot products of column vectors are 0. You can also, if you want, you can also try and invert, sort of transpose it and then multiply it with itself, but that's not necessary. This calculation suffices. In fact, if you try and transpose it and then multiply it with itself, I believe you'll be doing extra calculations along the diagonal entries, which you don't need to find. Or it would be faster to just like check the norms of each of these column vectors anyway. But to be fair, any method is fine with you. So we make sure that the vectors are orthogonal, and we check their norms are all equal to 1. Cool. So for an orthogonal matrix similar to 1, the eigenvector corresponding to eigenvalue 1 is the axis about it which it rotates. So this is how we find the axis of rotation. For an orthogonal matrix, which is a reflection and a rotation, right? So we have an eigenvector which corresponds to eigenvalue 1, eigenvalue -1, and this is going to be the axis of rotation again, but also this time it's going to be perpendicular to the plane across which it's reflected. So again, if you find the determinant is 1, you check the eigenvector for eigenvalue 1, that's the axis of rotation. If it's -1, you find the eigenvector of eigenvalue -1, and that'll be the axis of rotation, and the plane which it's perpendicular to is the reflective plane. So the rotation, angle of rotation, recall, you use the trace and calculate inverse cosine, rearrange this and find alpha equals inverse cosine -5 on x, 5 on 6. And so to summarize this, the angle, and to find the axis, you just find the eigenvector using the kernel calculation. I won't do it here, but it's 2, 3, 2. That's the vector. And so this is the axis. Cool. Conics and quadrics. Conics and quadrics refer to like the set of shapes, defined in like this form here, like ax squared plus by squared plus cz squared plus some like xy xz terms and like a constant term. So this is pretty complicated for like a 3D expression. Usually you only be given 2D expressions in the exam, but I haven't encountered a 3D expression ever actually. But one such, like one such shape is like the circle, or let's say the ellipse, which looks like, here's one such equation. If you make this plus or minus sign, you get a hyperbola. Wait, no you don't. Yeah, you get a hyperbola. Okay, cool. Yeah, these are like the signs which determine the surface, but honestly, you don't like need to know them that well. You kind of just need to be able to identify ellipses and hyperbolas of 2D, and obviously circles as well. So it gets more complicated when you have like x, y, y, z, and x, z terms. That's when it's like more difficult to determine. There's some methods which are taught where like you group certain factors into squares. So like if you have like x squared minus 2xy plus y squared, right? You can like group that part up, and that becomes a square. And then you can like rearrange in different ways. But the best way to do this is actually to use theory of matrices. So let's take a conic surface here. We want to find its principal axes, the type of surface, and the points which are closest to the origin. Okay, so our method for going about this, this was also taught in the lecture, so feel free to go over this, but basically we want to write the curve in this form, xtax. So x is going to be a vector of the variables x, y, and z, like this. So that's going to be the vector x, and it turns out when you multiply them, if you try and multiply this entire thing out, which we'll show, you can express any quadric surface, like for example this one. We then want to find its eigenvalues and eigenvectors, and then we want to diagonalize A, so that when we expand this out into the xt form, notice that xt and q, and also x and qt and x will be grouped together, and these are both transposes of each other. So we can write this in another way, which also represents a similarity transition. So firstly, the first step, xt, ax. So notice that if we try and compute, see how this whole thing gets computed out, we have a matrix here, 2, 4. When you try and expand this product out, the matrix times the rightmost vector will be another row vector. So that's going to be x times the first column vector. So let's say I just write this as column vectors. So this is going to be x times the first column vector plus y times the second column vector and z times the third column vector, right? And all this is going to be one huge row vector. Then what you're going to do is you're going to multiply them row-wise here. So what each of these entries are going to correspond to, right, is going to be, this is going to be the x squared terms. This is going to be the y squared term, and it's going to be the z squared terms. You can try doing it like this, where you put x, y, z, and x, y, z, like this. You see the x squared, y squared, and z squared terms are 5, 3, 4. So you put 5, 3, 4 along the diagonals. Then the xz and yz terms, right? You actually have to evenly split them out, because in your matrix multiplications you have two equal entries, this 2 and the 2 here. So what you do is you have 4 and you divide it into 2 and split it evenly here. This yz you evenly split here and here, 2 and 2, and then there's no yx or xy terms. So you leave those as 0. So what you end up is basically this matrix over here, this A matrix here. So I'll write this x, y, z out. Cool. So this is how you calculate the matrix A given the curve. Then you can calculate the eigenvalues and eigenvectors. Eigenvalues take the characteristic polynomial. Eigenvectors find the kernel of A minus lambda I. So here we find the eigenvector for eigenvalue 1, eigenvector for 4, and eigenvector for 7. So now we can diagonalize. Here's a reminder of our steps. So when we try and diagonalize this, first make sure you put each of your vectors in normalized form. Q has to be an orthonormal set of column vectors. That's what it means to be unitary or orthogonal. So you have these vectors listed here, and so you can write like this. So this is the way you do spectral decomposition. You write your eigenvectors in the order of the eigenvalues listed along the diagonal, and then you have your inverse matrix here. In this case, for a unitary matrix, the inverse is equal to its transpose. So we can just write t instead of -1. So recall that this is going to be the expanded form. So as I've noted, the qt, the xt and q and the qtx group together, and they're transposes of each other. So we can group them up like this. And we substitute x, the big X, equal to this qtx. So what ends up happening is that you have qtx times this x, and what you can do is you can basically write this in terms of this. So now you have variables big X, let me do this again, big X, big Y, and big Z, like that. Notice that Q is a unitary matrix, or an orthogonal matrix. And remember what we said about 3 by 3 or 2 by 2 orthogonal matrices, right? These are all going to be rotations or reflections of each other, right? Including the 2 by 2 matrix. So what this corresponds to basically is we're saying that this big X here, right, is a rotation, or with some reflection composition of the small x vectors, right? So this equation here that we end up getting, where we take the diagonal matrix, right, and it directly allows us to expand as x squared, y squared, z squared. This equation here is a rotation of our original equation, all the way back here, this equation here. So this surface here is an ellipsoid, right? It's the x squared, y squared, z squared form, but there's some scalar factors in front. So we find it's an ellipsoid. This is it graphed. You don't need to graph it, obviously. But it's important to note that you now know that these are rotations of each other. So to find the principal axes of this quadric surface, you can basically do what you do normally for finding the axes of a rotation. So this is how the 1, 0, 0 axis gets mapped, right? So this is the first standard basis vector, the second standard basis vector, and the third standard basis vector. So these represent the normal XYZ planes. And then to find the new principal axes, you see how it's rotated by Q. So you see where each of these three standard basis vectors get mapped by Q, and that becomes your new principal axes. Cool. So yeah, the calculations, we'll see if they're done, but these will be the three vectors. Cool. And one more thing, yeah, it looks like it's done. So we also want to find the points closest to the origin. So these are going to be your principal axes after you calculate Q times each of them. The point closest to the origin, 0, 0, 1 over square root 7, that basically comes from this equation here. The closest point here is 0, 0 square root 7, because it's like, you can imagine the closest point is going to be like this, or like this, like the outermost points. You can see like it's going to be closest either for like 1 on 1, 1 on 4, sorry, 1 on 1, 1 on root 4, or 1 on root 7, because like all of these are solutions. 1 on root 7 is the smallest, so that's going to be the closest. And so then this is the closest point for your transformed equation, your rotated equation. So you need to perform the rotation back to get the original closest point. Cool. Great. So note how our table of signs have changed. All right. So a single value of a m by n matrix is a square root of the eigenvalue of a star a. You might be wondering, wait a minute, what if we take the square root of a negative number? Fret not. The eigenvalues of a star a are always going to be non-negative, so you can always take the square root of them, which is a fun property. So we define something called the singular value decomposition. So this is a different way to decompose a matrix, apart from the spectral decomposition method, where you line up the eigenvectors and eigenvalues that you did in your first year. In this case, SVD uses singular values, and it can be done for a non-square matrix. It can be done for any matrix A, which is pretty cool. So the requirements are U is an m by m matrix, V is an n by n matrix, and in the middle we have a sigma matrix here. I also notice this is V adjoint. We have a sigma matrix here, which is an m by n matrix sitting in the middle, with the entries of these singular values. So what you actually do is you get your non-zero singular values, right? So if this is like a long matrix shape, like an m by n shape, where m is less than n, then what you do is you start filling your singular values, say they're like 3, 1, 2, and then you put all of the other remaining entries, like here, 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 and also here, you put them, oh, also I should say the singular values have to be listed descending, but we'll get to that. So you put them as 3, 2, 1, and then you put all these other entries as zeros. If the matrix is taller than it is wide, so your original matrix A is taller than it is wide, sigma has the same dimensions, you put the entries here, so like 3, 2, 1, again, singular values are descending, and then you fill the rest as zeros, something like that. Cool. So that's basically what this rule here is stating. So here is our algorithm for finding the SVD. We want to find all the eigenvalues of A star A, which are non-negative, and we want to write them in descending order. And then we want to find their associated eigenvectors. Make sure to normalize them, so make sure they're of unit length. Then we compute the UIs. So V contains our eigenvectors. Specifically, we take V adjoint, but V will contain our normalized eigenvectors. U will contain these vectors over here. Basically, they're going to be A, our original matrix A, times each eigenvector. Notice the eigenvector is for this, not A. We take A times each eigenvector Vi, and we divide it by the square root of each eigenvalue. Note this is 1 over each singular value. And also, just a quick reminder, write your singular values in descending order. So write your eigenvalues in descending order. So then we extend UI as needed to fit the m by m shape, because some of these eigenvalues might be 0. So for the non-zero eigenvalues, you compute these UI, and then you extend with Gram-Schmidt to get an orthogonal basis. You form U and V with the UI and Vi matrices as mentioned, and you form sigma with the singular values that I described before. Okay, so let's try and do an example. Also, it's worth noting that A star and A share the same non-zero eigenvalues, except that the difference being that the A star, the A, or the bigger matrix, will have extra 0 eigenvalues in it. So it will have the same non-zero eigenvalues, and it will have some extra 0 eigenvalues to pad out the dimensions of the matrix. So this is useful when n is greater than m, since A star A is an n by a matrix, whereas A star is an m by m matrix. So it's going to be smaller. So particularly, we want to find the eigenvalues of A star, not A star A, because A star is actually just going to be a smaller matrix. When we multiply it out, it's going to be a 2 by 2 matrix, which is going to be easier to find the eigenvalues of. And then we say explain why the eigenvalues in part 1 are also the eigenvalues of A star A. Just state this lemma over here. And then we want to find all the eigenvectors and the SVD. Okay, cool. So we calculate A star, and we find its eigenvalues, which are these. So the way we do that, you can use whatever you want, characteristic polynomial, or find the trace and determinant. Part 2, quote the lemma. Just directly quote the lemma. Notice that it's going to share the eigenvalues of 12 and 10. A star and A is going to have 12, 10, and it has to have one more to pad out to a dimension to be a 3 by 3 matrix. So, sorry, it has to have an eigenvalue of 0. Cool. And part 3, part C, whatever, we want to compute the A star A matrix, and then we can, find its eigenvectors. So, quick tip is that. So here's a quick tip. We know the third row. So when we're trying to find the eigenvector by taking this A star A minus 12i and then finding its kernel, we know the third row must reduce to 0. You can verify this by trying to check for a linear combination. You can see if you multiply this by 1, if you multiply this by -1 and you multiply this by -2 and then add them together, you'll get the third row there, so you can express it as a linear combination. So this will row reduce to a bunch of zeros. And then you can find its eigenvector by row reducing and then, solving for the kernel in your augmented matrix. So that's for lambda equals 12. You find that eigenvector. For lambda equals 10, you find this eigenvector. Again, A star minus A star A minus lambda I. And then for lambda equals 0, You do the same process. You find the kernel of just the original A star A matrix, and you see it's spanned by only this eigenvector. Cool. All right. So now, remember, make sure list your eigenvalues in descending order. So 12, 10, 0. Part 4, part D, normalize your eigenvectors. They have to be of unit length, recall, and then you want to calculate your UIs. So we have, for this V, we can now construct our V. We have the singular values to construct our sigma, and now we want to construct U. Okay, so we can construct V adjoint, sorry, yeah. And now to construct U, we calculate U1 by taking A times VI, and then dividing by the singular value, which is the square root of the eigenvalue. So that entire, this part here is the eigenvector. This is A, and 12 is your singular value. So that multiplies into that. Similar process here, and you don't do this for 0, because you can't take 1 over 0. And we conclude that this is our singular value decomposition. Note we don't need to extend U because we A star didn't have any 0 eigenvalues, or another way to say it is this will form a 2 by 2 matrix, which is what we want anyway. So we get U, sigma, and V, from which we can calculate V star. Cool. So yeah, if you feel free to rewrite V as like V transposed, which is just V star because there's no complex numbers. Cool. Yeah, that's going to end the chapter on eigenvalues and eigenvectors. Let's move on to Jordan form. So Jordan form is going to be an extended way, a way to generalize the notion of diagonalization, because we can't diagonalize any matrix, but if we have a complex matrix, we can write it in a Jordan form, a square matrix, that is to say, where we want to try and replicate the diagonalization process as much as possible. So this is our Jordan block. This is what we define a Jordan block as. It looks like a diagonal matrix. So like this looks like a normal like set of like eigenvalues almost with lambda, 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 and ones along the superdiagonal. So the superdiagonal is the quote-unquote diagonal, so all the entries which are right above the main diagonal. So like if we have 2, 2, and 2, like this along the diagonal, the superdiagonal will be this set of ones here, and we have a 0 here. So the superdiagonal is going to be this 1 and this 1. Okay, so here's some examples. The subscript denotes the length of the Jordan block, and the inside represents the eigenvalue. So it's going to be of the form jk lambda, right? So here's 1 for -4 with length 3, and here's 1 for 0 of length 4. So if we try and exponentiate a Jordan block, try and see the pattern, you can guess like, for 1, like a Jordan block with length 1, it's just lambda to the n. Then you introduce this binomial coefficient, and then this one here and this one here. The other entries are going to be the expansion of 1 plus lambda to the n, and you take like the next lambda to the kth most coefficient and its respective element, and you try and fill in the Jordan block as much as you can. So if you ever stop, so like you put down lambda n, and then you put down the next binomial, decrease the power, and then you keep on going, it's worth noting that if you stop, right, or like if you ever reach n on n, choose n, the rest of your entries are going to just be 0. You just put 0 everywhere else. So as an example, if we let, for the j for lambda to the n case, if we let n equal to 2, right, this is all going to be fine. This is going to be squared, right? This is going to be taken to the power of 1, like this. So yeah, let's just write this out. This is going to be squared. This is going to be taken to the power of 1. This is going to be 2 choose 2 times 1, which is just 1. This entry here, so like this whole thing is just going to be 1, 1. So this here was lambda squared. This is n lambda. This top rightmost element is going to be 0. So just to like show that if n equals 2, this is going to be 0, because this is past 2. Okay, so we're going to define the direct sum of matrices. This is different to eigenspaces. Basically, when you take a direct sum, you're composing the matrices into blocks. So what you're doing is you're putting them along the diagonal, the matrices along the diagonal, and you're going to expand them out. So we're just going to worry about this for like square matrices and specifically the Jordan blocks. But here's some examples. If you have J23, notice this block, and J45, this block, notice firstly the order, and notice secondly how they're placed. They're in the diagonals, so their diagonals, right, the diagonal elements are still in the main diagonal, and the super diagonal is also just so happens to be in the super diagonal. Notice there's nothing here. Cool. And it turns out when we take the direct sum, this is really useful because when we compose Jordan blocks and we take them to the power of n, we can separate each of the exponents out to each of the Jordan blocks. So as an example, if we were to exponentiate this direct sum of Jordan blocks, we can exponentiate each of the parts. So instead of like exponentiating the whole thing and getting something weird, we can just exponentiate this. And this is a consequence of the direct sum, the fact that it's on diagonal elements. It turns out a lot of properties of like direct sums and like block matrices carry over from their normal matrix counterparts. For example, like when you exponentiate a diagonal matrix, like this, you just exponentiate the diagonal elements like that. And that's the same, almost like the same for the direct sum. This is going to be really useful because we can write any matrix. We're going to show that we can write any matrix. Like we're going to, it turns out you can write any matrix as the sum of Jordan blocks. So maybe of like something like this. And so when you exponentiate it, you can exponentiate the individual terms. So I'm going to define the notion of generalized eigenvector to do this. So recall that a normal eigenvector is such that a v is equal to lambda v, or written in another way, this, right? And so to generalize this, we say if we take a minus lambda I to the v equals 0, that's an eigenvector. But if we do that again, so if we do that twice and we have to get to 0, we say that's a generalized eigenvector. Or if you have to do it 3 times, and then 4 times, and then 5 times, so on. So a minus lambda I to the k times v equals 0 is a generalized eigenvector. So here's a question where we want to show that given this matrix in V, it's a generalized eigenvector. So all you have to do, like I said, is take a minus lambda I, apply it to V once, see if it's 0, then apply it twice, see if it's 0, and keep doing that until you get 0. So you won't always get 0, but this question kind of says show it's a generalized eigenvector. So you can be like, you can rest assured you will get 0 eventually. So we compute it once, we get -1, 1, and we compute it twice, and we get the 0 vector. So that means that V is a generalized eigenvector, corresponding to lambda equals 5. Okay, so generalizing the notion of an eigenspace, we get the generalized eigenspace. So as you might guess, it's just the vector space of all eigenvectors, which correspond to this eigenvalue here. Here's another way of writing it. Technically, anything in the kernel of this is going to be in the kernel of this, and so on. Like the kernel of this is going to contain elements of this. So really, you don't need these parts, but it's worth noting anyway. So really, each of these parts here is going to be like the kernel of this lambda I squared, but that doesn't include a minus lambda I. And then so on. This would be cubed minus set minus a minus lambda I squared. So we want to link these properties here. We want to link the properties of a generalized eigenspace to a Jordan matrix. And we want to show, like, again, we can decompose any complex matrix in this form, and we want to, like, mimic it as much as possible. So we say that it's a complete similarity invariant, which means that if you want to classify two matrices as being similar, all you have to do is check if their Jordan forms are equal, and that's it. And it's an if and only if. So if their Jordan forms are equal, they're similar. And if you, yeah, whatever. If they're similar, then their Jordan forms are equal. Okay. So the way we're going to do this, so also worth noting that every matrix A has one Jordan matrix up to a permutation of the Jordan blocks. Yep. So this is kind of like factorization in a way, which is interesting. So we're going to define some properties which will allow us to restrict like the possible numbers Jordan forms can be. So if we set dk to be equal to the nullity of a minus lambda I to the k, and we set like for d0 it's equal to 0, then we notice again, like I mentioned before, the previous ones are going to be the subsets of the next a minus lambda to the k, right? So what must happen firstly? This is this first property is kind of clear. The dimension of the a minus lambda I to the k, right, kernels has to increase. Okay, so something like 1, 2, 3, 4. So this could represent the nullities of a minus lambda to the 1, to the 2, to the 3, to the 4. A much more interesting property is this one here, which says that the differences are non-increasing. So, sorry, this second property says that the differences are non-decreasing. That means they're either going straight or up, or straight or up. But this one here says that the differences are either going straight or down, straight or down. So by differences, I mean, here's an example. If we were to give something like a sequence like this, like 3, I'll just put the 4 back here, like 3, yeah, let's go with, start with 0, 0, 3, 5, 6, 7, 7, 7. Notice that if the sequence is non-decreasing, so it's increasing and then it stays straight, it never goes down. That never happens. But note the differences. So first it jumps by 3, then by 2, then by 1, then by 1, then 0, 0, 0, 0. The amount you jump by never increases. It's either going down or it's going straight. That's what we mean by that. So one consequence of this is that if you have a sequence of increasing Jordan block dimensions and then it suddenly goes straight, this means that the Jordan block dimensions can never change again. Sorry, I shouldn't say Jordan block dimensions. These dks can never increase again. So if your dks increase and then stay the same, they can never increase again. They'll always be static at that point. So as an example, let's take this matrix here, C. So we get these eigenvalues 3 and 5. If we were to try and look at their sort of their kernels, right? We take C minus 3i. This is for eigenvalue lambda equals 3, which note has algebraic multiplicity 3. The nullity is always 1, okay? Because there's always 2 non-zero rows. For the eigenvalue of value 5, the nullity is going to start off as 1, then it's going to go to 2, and then it's going to go to 2, and you can actually probably guess that it's always going to stay as 2. And the reason why is, like, again, it turns out like the difference in a minus lambda I dimensions, right, dimension differences, is going to be non-decreasing, and this is a non-increasing, and this is a non-decreasing sequence. So this goes up and then always stays the same, because the difference is 1, then 0, etc. So this is sort of the text description for this. So note that the nullities terminate at some maximum value. This is a really key property. It turns out this maximum value is actually going to be equal to the algebraic multiplicity. What this means is that the generalized eigenspace, it'll grow and then terminate at some point, as we described before. And if it terminates at the algebraic multiplicity, this means that we now have a way to characterize the entire space of that your matrix works in. So the dimension of the generalized eigenspace is equal to algebraic multiplicity. That means that if you take the direct sum of all of your eigenspaces, not matrices, right? This is different direct sum. If you take the direct sum of like one eigenvalue and then another eigenvalue, say like mu, and then you do that for every single eigenvalue, something like this, right? So you do this for all of your eigenvalues. This must be equal to your original vector space that the square matrix is applied on, or the linear map is applied on, because it's equal to the algebraic multiplicities, and we know the algebraic multiplicities add to n, which is a really interesting property, because we had that the geometric multiplicity is less than or equal to the algebraic multiplicity, but we now have like a nice way to see this. Like we have the geometric multiplicity is the first jump in dimension, and we have like some barrier which could be the algebraic multiplicity. Either we hit the barrier immediately in the first jump, so gm equals am, or we have to make a bunch of jumps until we get to am. So we define this notion of Jordan chains. Basically, this means like recall the process of applying a minus lambda I to a vector, and you constantly do that until it gets 0. So we write the Jordan chain in this direction. So the Jordan chain decreases to 0, but we write the Jordan chain backwards. So v1 in this direction. So v1 to vn. So this corresponds to one Jordan block. We'll see some examples of this, but a useful way to like explain all of this is like block diagrams, because it's very easy to get lost in the source, because there's a lot going on. So a useful way to like see like how the dimensions grow, but also to see like how you construct your Jordan chains, is to use block diagrams. So I'll show this with an example, and also worth noting that the overall structure of the like this can also be used to like show the structure of how lambda I contributes to the Jordan matrix for its particular Jordan block. So let's see why this set of nullities is not possible. You can use the rule before about the non-increasing differences. That will directly solve it, or you can use your block diagram. So the way you draw your block diagram is this is done in different ways. I'll do this like by going vertically and then going left. So your first block, you're going to draw the first set of nullities. So you're going to draw 5 blocks, right? You're going to stack 1, 2, 3, 4, 5 blocks on top of each other. This is going to be, the dimension of your eigenspace, like your normal eigenspace, right? And then you have 8. 5 increases to 8 by 3. So I'm going to put 3 more blocks here. So now I have 8 blocks. And then when I go from 8 to 9, I'm going to add 1 more block, 9. So at this point, if we were to stop here, these would be this is your like Jordan block diagram. This is your geometric multiplicity, this here. The height is this, right? It's 3. if we were to stop here and it was just 9 forever, so there's going to be no more blocks, this here refers to your height. So it's 3 here. That refers to like how many times you jump until like you never go higher. And your Jordan chains are going to be like this. So your Jordan chains are written in the opposite direction. They're going to start from the space of like your eigenvectors, and they're going to jump up as you sort of like take a vector, apply a minus lambda I, and then go backwards. So this is like one such Jordan chain, v1, v2, v3, and here's another one, here another one, another one, another one. However, what we have is that we actually keep going. So we get 9, and then we get 12. That means we have to add 3 more blocks. 1, 2, 3. And then we get 12 for the rest of the thing, so there's no more. The issue with this diagram is there's actually a gap in the middle. So for one, we can't have gaps in the middle. But also, secondly, if you try and draw your Jordan chains, like whatever direction, you notice you can't get past this gap here. So you can't get past these 2 gaps here. So this can't happen. So your Jordan block diagram can't look like this. It has to look like some sort of staircase for it to be valid. So this is never possible. Okay, so here's another question. We get these nullities, but this time we want to find all possible Jordan forms. So the way we would do this is, draw your block diagram. You draw 1, 2, 3, 4, 5 blocks for your eigenspace, like your space of normal eigenvectors, like for 1, k equals 1. Then you draw 3 more for the 8, 1, 2, 3, and then 1 more, 9. So you draw your final block here, okay? And notice you don't know if there's going to be any more. So there could be a block here, or there might not be a block, okay? So notice it's a 10 by 10 matrix. That means you can only ever add 1 more block, right? So, because that's like the dimension of your space. And all of these linear eigen blocks represent different generalized eigenvectors, which are all linearly independent of each other, right? So you either add, for this eigenvalue, you either have a block here, or you don't. Notice you can't add a block here, because we know that for 3, the nullity was equal to 9. This would, if we add a block there, this would imply this nullity here for 3 is 10, which is not possible. So we either add a block here, or for a separate eigenvalue, say mu, we have another block, but we can't have any more blocks. So either 9 blocks plus 1 extra here, or an extra block for mu, and there's nothing else because that adds up to 10. So to represent this as like different Jordan forms, the one way you have everything as one eigenvalue is you have j. You sort of represent this as like the Jordan chains. So each of your Jordan blocks is going to be like a Jordan chain, which is kind of confusing if you like don't distinguish this block, like each of these individual blocks from like actual Jordan blocks. So think of like now what the Jordan blocks I'm talking about as like Jordan chains. So let's try and redraw this. 1, 2, 3, 4, 5. So in the case where we have 10 individual pieces, these are our Jordan chains. So one possible Jordan form is we have a Jordan chain of length 4 for the eigenvalue lambda, direct summed with the Jordan chain of length 2, lambda, and then another 2. So there's 4 here, 2 here, 2 here. So Jordan 2, lambda, and then direct summed with J1 lambda, and then direct summed with 1 more J1 lambda. Okay, so that's one Jordan form. The other one is where we have lambda. We have a block for mu. So we don't have this block, and it's a block for, say, mu. Let's do it something like that. So then in that case, you have a Jordan chain of length 1 for mu, and then you direct sum it with J3 lambda, and then J2 lambda, because this is 3, this is 2, this is 2, this is 1, 1. So you do J3 lambda, 2 J2 lambdas, and then 1 J1 lambda. And you can just say, like, don't worry about permutations of these. You can just say, like, and all permutations of these also count. Though it's worth noting that this J1 should be separated from these J3s. But yeah, you don't have to worry about that. So those are the two possible Jordan forms. Cool. Here's another question. We have a matrix C and V. I think these are original matrices. Yeah, from example 1. We want to calculate C minus 5i and C minus 5i squared V. This seems to imply that V is a generalized eigenvector. Otherwise, why would we? This is a very suspicious calculation, very similar to generalized eigenvectors calculations. Then, without any matrix calculations, we want to write down the algebraic and geometric multiplicities. Yep, and finally, we want to. This wasn't in the exam, but we want to actually Jordan decompose this. So we haven't talked about how to construct the matrix P, but it's not too bad. So, yeah, so the trace is usually helpful because it's the sum of eigenvalues. And note, like, firstly, for part 1, we already saw that this is non-zero and this is a zero vector. So this is non-zero. This is really important, by the way. This is non-zero, but this is the zero vector here. Okay, so I'll just say this is equal to 0. Zero vector, non-zero vector. Secondly, we know that 5 is an eigenvalue. We also know that 5 is an eigenvalue of algebraic multiplicity 2, of at least algebraic multiplicity 2. This might not be so clear as to why, but basically the idea is you can imagine, like, your block diagram if you want, or like your increasing set of decays. Okay. If we had the algebraic was 1, algebraic multiplicity is 1, right? What that would mean for eigenvalue 1, what that would mean is that you never have a minus lambda. If you have a generalized eigenvector V, it must actually just be an eigenvector. Okay. The reason why is because when you go from the kernel of a minus 5i to a minus 5i squared, we see that for V, which we know now is a generalized eigenvector because of this property, we see that it starts off being non-zero and then it's equal to 0. That means that the dimension must jump by 1 because we actually have a generalized eigenvector which jumps up twice. Put another way, we have a Jordan chain of length 2. The Jordan chain, here, let me scroll down, the Jordan chain being this. You get your original vector V, you apply it once, and that's like your two Jordan chain vectors. So we know that the algebraic multiplicity must be at least 2. So that means there's 2 instances of the 5. Okay, so this is pretty good, actually, because now we can just directly use the trace to find the third vector. We only have one missing eigenvalue. Remember, if you have one missing eigenvalue, just calculate the trace, and we find lambda 3 equals 3. So for lambda 3 equals 3, right, we know that am for 5 is at least 2, and for 3, it must be at least 1. Because we've completely filled out the space for a 3 by 3 matrix, right? We have something that's at least 2 and something that's at least 1, and they have to both add to 3. They must be equal to 2 and 1. The algebraic multiplicity here is 2, and the algebraic multiplicity here is 1. 2, 1. The geometric multiplicities are both 1. So in this case, for 3, it's clear why the geometric multiplicity is 1, because gm is less than or equal to am. For 5, it's not so clear. But remember again, when we took this Jordan chain, we jumped up to a non-zero vector and then a zero vector. That must mean that the geometric multiplicity can't be 2, because we actually increased in dimension before we got to the algebraic multiplicity. If we stopped immediately, so if we went 0, then 2, then 2 in like our decay diagram, we would have no generalized eigenvectors, which are not eigenvectors. But we can like see that this is not an eigenvector, because this is not 0, and yet it's a generalized eigenvector. So this is all to say, like, the geometric multiplicity jumps up in your decay sequence. So you get this list of values here. Anyway, to find your eigenvectors, because that's like, yeah. So you want to find the eigenvector for lambda for eigenvalue 3, because we want to write the matrix P. We want to find its generalized eigenvectors. For 3, it's just the eigenvector, so you just find the kernel of this. So it's that. For eigenvalue 5, you know that this is a vector, and so then you compute its Jordan chain, like we've done before. And you remember to write your Jordan chain in backward order. So you write this eigenvector here, and then your original vector, and you write the Jordan block corresponding to it. So each Jordan block corresponds to a Jordan chain. And you could have like multiple Jordan chains for a given eigenvalue. Like remember from your block diagram, like your block diagram for this like eigenvalue 5 could theoretically look like this. So you find, so in this example, what you would do is you find this Jordan block and you find, you know, this Jordan chain and this Jordan chain. Let's say you get like V U is your Jordan chain and this is W, and this is like eigenvalue 5. What you do, your matrix J is you write one Jordan block, let's say for eigenvalue lambda. You write one Jordan block, which is this, for a Jordan chain of length 2, and then you write a second chain for a Jordan block of length 1. Yeah, and so you, yeah, for eigenvalue length 1, and then your set of matrices, give me a second, your set of matrices, so you have lambda 0, 1 lambda, lambda, and then you filled everything here as 0. Okay. It's getting a bit janky. Wow, okay. So that's going to be your Jordan block. Just imagine there's a 0 on the top right. And then your transition matrix P is going to be like, you know, it's going to be U and V corresponding to this Jordan chain, and then W corresponding to that other Jordan chain. So there's a lambda there. Okay, I don't know why this is not cooperating. It's all getting like stuck here. Okay, that's what J looks like, and P looks like U, V, one Jordan chain, and W as the Jordan chain for this. Cool. But we don't have to do that, we just get this here. Okay. Here's another question. We take a matrix A. We're given two generalized eigenspaces for eigenvalues 2 and 3. And we're asked to find the Jordan chain for lambda equals 2, starting with 0, 1, 1. Okay. We can actually probably guess, like, if it's trying to ask us to find a Jordan chain, it implies like the length is greater than or equal to 1, and it actually goes to like this vector here, or something along those lines, like a scalar multiple of this, but no need to worry about that. We'll just do this question normally. So we find the Jordan chain for this vector here, and without calculation, we want to find the geometric multiplicity. It's going to be similar to what we did before, and then find the Jordan form and invertible matrix P. So how do we find the Jordan chain? We apply a minus 2i. You apply the corresponding a minus 2 lambda i, a minus lambda I for your eigenvalue lambda. So in this case, it's 2. You get a Jordan chain of length 2. Then part 2, write down the geometric multiplicity of lambda equals 2. Again, Note that the algebraic multiplicity in this case is actually is the geometric. Yeah, so the algebraic multiplicity is like the dimension of the generalized eigenspace, which is 2. So AM is equal to 2. Okay, now GM is less than or equal to 2. So it's either 2 or 1. It can't be 2 because that would mean this is immediately an eigenvector. But it jumps up in length, in dimension. It jumps up in dimension and then goes to 0, which means that GM must be equal to 1. Actually, it's going in the other direction. The space of eigenvectors must jump up in dimension to get to a generalized eigenvector. Undoing an application of A minus 2i. Cool. So we get GM of this is equal to 1, and we want to write the matrix P and J. So J here, this corresponds to the Jordan chain of length 2 for the eigenvalue 2. Notice that it's in backwards order, so it was 0, 1, 1, goes to -1, -3, -2. This is that Jordan block here, the eigenvalue with the superdiagonal, and we have another Jordan chain of length 1, which is just a single vector. That just corresponds to this 3 Jordan block of length 1. Okay. So now, final part, surprise question. We want to find V here and W here such that V plus W is equal to 2, 1, 0. Okay. So this might be a strange question, as if it's like asking us to as if it's asking us to as if it's assuming like there's always V plus W equal to 2, 1, 0. And again, note, this has been stated before, but because the algebraic multiplicities correspond to the dimensions of the generalized eigenspaces, the direct sum of the generalized eigenspaces must be your entire space, written exactly here. So that means that you can actually just take combinations of linearly independent GE vectors and get any vector you want. So the way you do this, I won't, I'll like briefly explain that basically you take this matrix here, P, right? That's gonna, P literally represents your set of linearly independent GE vectors, and you solve when this is equal to 2, 1, 0. So you solve this matrix equation here by row reducing, and you find the linear combinations of vector 1, 2, and 3. And it asks you for V and W. So W would just be a scalar multiple of this. V would be like some linear combination of these two Jordan chain vectors over here. Cool. So it's not always the case that the question tells us which vector to start with to find a Jordan chain, but it turns out because generalized eigenspaces are bigger than the lower order subset of generalized eigenvectors, like the smaller kernel, you can imagine a plane is infinitely more likely than a line, but we're only working in integers of certain sizes, whatever. You're very likely to find a vector that where such is the case. If it doesn't work, just cook up, cook up your own initial vector. If it doesn't work, try again with another vector. You probably won't get screwed over. Okay. And it's and the way you find a generalized eigenvector is by analyzing the kernel of a minus 2i to the whatever power. So in this case, a minus 2i here is equal to this vector matrix here. And we want to find some vector t where this is equal to an eigenvector, but applying the eigenvector gives us 0. So we want to find something of order 2. And one way you can do this is just by taking a minus 2i squared, finding the kernel of that and doing some more analysis, or if you want to be safe, you can cube it to see if the dimension changes. Just a sort of slightly bashy question, but shouldn't be too bad. I won't go over the calculations, but this is essentially the method. Like calculate a minus 2i squared, find an eigenvector, calculate a Jordan chain of length 2, and Bob's your uncle. Cool. So Cayley-Hamilton. This is a cool consequence of, well, there's a few ways to prove this. One way is with Jordan matrices and Jordan forms. So let's say you have your characteristic polynomial here. Your eigenvalues when you substitute them in. Oh yeah, here, sorry. This is the actual Cayley-Hamilton theorem. So when you substitute eigenvalues into your characteristic polynomial, they equal 0 because they're the roots. But it turns out if you substitute the matrix, because you can exponentiate it, you can exponentiate matrices, you actually just get the 0 matrix, which is pretty cool. And there's like a more specific version of this theorem involving minimal polynomials. Like briefly to explain, from the description of the height, which I mentioned before, which is like the length of your Jordan block diagram, if you have like your eigenvalues here like this, and maybe you have them like squared and cubed, you can replace these with these algebraic multiplicities here with the heights of each eigenvalue. So this could be height h2, and this could be like h3. So this represents the longest Jordan chain. And it turns out if you substitute A into this, right, your original matrix into this with like the original Jordan chains, you get 0. You get the 0 matrix as well, which is a more specialized case of this. To summarize again, like if you take the characteristic polynomial, replace it with the heights of each of the eigenvalues, i.e. the length of the longest Jordan chain, and then substitute A in, right? So the polynomial you get where you replace the exponents with the heights is called the minimal polynomial. Then when you substitute A in, you'll get 0. Yep, cool. So we have this question here. So we're given a characteristic polynomial, and we're given a v that's in the image of this really weird quadratic. And we want to use Cayley-Hamilton, right, to prove that v is an eigenvector of eigenvalue 1. So you might sit here scratching your head like, what? Okay, Cayley-Hamilton I substituted into this, but what does this have to do with anything? I'm confused. Well, the idea is like, an eigenvector of eigenvalue 1 is such that if you apply t minus lambda to it, you get 0, right? That's what it means to be an eigenvector, right? So you have this t minus lambda here, and you also notice, okay, I actually have this quadratic t minus 4t plus 6i here. The idea is you kind of think to yourself like, maybe this has this quadratic as a factor, right? And if it has this quadratic as a factor, the other factor must be this. The idea is like, okay, so v is in the image of this quadratic here in terms of t squared. Then for some reason, when I apply t minus lambda, it becomes 0, right? So your intuition is to like expand this. And so you can actually verify this. So if you expand x minus 1, which represents like t minus I, like the notion of being a eigenvector, and if you expand and you take this quadratic and multiply them, you get your original cubic. So just to note, this cubic here was this cubic, this quadratic here was this quadratic, and the eigenvalue of 1 represents this. So now what happens? Note we can, because v is in the image of this quadratic, you can write v in this form. So t squared u minus 4tu plus 6u. So this is applying this linear map to u, right, for some u. That's what it means to be in the image. Now we can see what happens when we do t minus iv, right? If we do t minus iv, we do t minus I times this matrix here, right? Notice recall the associative property of matrices, you can actually group these together. And this becomes the characteristic polynomial, and whoop-de-doo, you can use Cayley-Hamiltonian, because this is your cubic, this is your characteristic polynomial, this is always 0. This is always going to be the zero map, so this whole thing is going to give you the zero vector. And this means that V is an eigenvector with eigenvalue 1. Cool. Don't worry about this slide here. All right. So for the final topic, very short, or quite short topic, it's on matrix exponentials. So the exponential of the matrix, like the normal exponent, it's a sort of weird definition. You can take like the exponential of like a real number, but you can also exponentiate matrices if you define it in this Taylor series form over here. So it's important to note this Taylor series form. Let me just quickly check. Yeah, it's important to note this Taylor series form is just a glorified polynomial. And we actually get, very cool. We actually get a lot of the properties of the exponential carried over to matrices as well. So if you take x of a times x of b, you add the matrices, if and only if they commute. Kind of funny. This is usually like a defining property, but you only get this if ab equals ba. The inverse of xb is x negative a. This is pretty useful because it allows us to skip out on some calculations for inverses. And if you differentiate x of ta, you can basically just take the a out, as if you're differentiating as if a is a constant. Again, you can prove all of these properties by using the Taylor series, and note they all work because it's just a glorified polynomial, and especially like some of these about commuting stuff, like this one, and this one. Notice that xA and a commute because polynomials of a commute with a, and again, e to the a is just a glorified polynomial. Cool. Here are some more properties. So these are more like calculative properties. These aren't too important for like calculations in exam questions, but these are worth knowing if you want to understand them fully. So if you have a equals p inverse, this one is important. Exponentiating a will exponentiate the b inside. So again, this is to do with the polynomial property. If you exponentiate p inverse, say you take this to the power of n, this is equal to b to the n p inverse. And if you have a direct sum of matrices, so like that block form, then exponentiating the whole thing will exponentiate each of the parts. The reason why it's the case because you guessed it, glorified polynomial. Recall this property holds for exponentiating, and polynomials are just sums of exponentiations. So it also holds for e to the whatever. And if you exponentiate a Jordan block, you get this weird form here. So what happens is you take e to the lambda t, where lambda is for the Jordan block, and then you write 1's, t's, and then t squared on 2 factorial, and so on, t cubed on 3 factorial along the super diagonals. So basically, these are really just going to be the power series terms of e, right? So the power series terms are 1, t squared on 2 factorial, t cubed on 3 factorial, etc. You would have seen this in your first year. And don't forget to take out like this e to the 2t. Cool. So quick example. So recall like our C matrix from earlier. Say we want to calculate x of tc. We have p and we have j, and we want to, substitute in this form. We break it down into its Jordan forms as such, and we use the property that the exponential function distributes over a direct sum. So we apply the exponential to each of the Jordan forms using this bigger formula over here. Okay, and we direct sum with this one here. So notice the e to the 5t that was taken out and put back in. So what it was originally is like e to the 5t times 1, 1, t, 0, like that. That's what that would be. Then you direct sum by putting them along the diagonals, and hence xtc is equal to this. Cool. All right. If we have a Jordan chain of this form, then we actually have an easier time of calculating the exponential matrix times a Jordan chain vector. So remember from before that, like say you want to calculate xta times v1, right? This is a bit tricky to do if this can be a bit tricky if v was not a Jordan chain vector, and you didn't know it's like Jordan, or if you didn't know it's like Jordan vectors. What you might do is you might calculate x per ta and then calculate the matrix product. But there is an easier way to do this, and this is going to help us with a question type later on, where we want to solve ODEs using matrix exponentials. So notice what this form looks like. You kind of just have to memorize this formula. E to the lambda t is the eigenvalue, and in each of these parts you get the Jordan vectors multiplied by the power series terms. Note that it doesn't go all the way up to k, it goes up to k minus 1 because you start at 1. So 1v1, then the second power series terms times the second Jordan chain vector, and so on. Note it's now in this back. Whoops, sorry about that. Whoopsie. Okay. So note that this Jordan chain is in the order where it goes to 0, not in that reverse direction where you write the matrices, where you write it in the matrix P. So yeah, let's have a go at this. Well, let's just hope this live stream is still on. Okay, cool. Matrix exponentials are very useful for solving homogeneous systems of equations. So the solution to this equation with dy dt equals ay is going to be of this form. For some constant c, more specifically, when for the initial condition y0 equals c. So what this is nice for is if you have two sets of differential equations, or you have a two variable differential equation, something I don't know, let me cook up something y prime equals 1 minus x and x prime equals y squared. I don't know. Okay, it has to be linear. Something like y plus 1. Okay, let's throw an x in there as well. Oh, okay, actually this is also, okay, this is messy. Yeah, y minus x equals, and y plus x, something like that. You can write this as a Jordan vector, right? So you write y equals the vector y is equal to xy, right? And then you say y vector prime is equal to e to the so I guess it has to be a function. Let's just say this whole thing is multiplied by t, something. How does this work? Oh wait, yeah, this works. Yeah, so say you get y prime equals it would be 1, so it'd be -1, 1, and 1, 1 times y, the vector y. Okay, let me write this neater. So you have these two equations, y prime equals y minus x, and x prime equals y plus x. Yeah, so you have y prime equals y minus x, and x prime equals y plus x, right? If you note the vector y equals xy, then y prime equals -1, 1, 1, 1 times y, like that. Okay, and so that's in this form, and then you can solve this using standard techniques. So the homogeneous solution is, sorry, this form here. The homogeneous solution is if you take the exponential times the initial condition. Recall that for C and V we have this Jordan chain, and let's say we want to solve this homogeneous equation here with y0 equals v. This is actually pretty straightforward because you just use this formula back here. You take x per ta, or e to the ta, and you multiply it by your vector v. And we know how to do that. If we multiply a Jordan chain vector, it's in this form where you take the first Jordan chain vector times 1 plus t times the second Jordan chain vector, and then you multiply by e to the 5t. If there were more terms, then it would be t squared on 2 factorial and times the next vector, and so on. But you don't need to worry about that in this case. And so this is our solution. So you would get something like x is equal to the first function, y is equal to the second function, z equals the third. Right. Let's see. This gets a bit trickier when we do inhomogeneous equations. We have to use a method. So this is the inhomogeneous part. We have to use a method known as variation of parameters to solve this question. So what we do is we guess at a particular solution. We say y is in this form, the exponential matrix TC, x of TC times z. And we get that on the right-hand side of this expansion. We can use the product rule. Remember that differentiating a function with exponentials, you can treat the exponential as a constant. So you get the c at the front. Notice that y equals c e to the tc. So these two terms here cancel out. And then you get this etc times z prime equals the inhomogeneous part. So if you divide both sides by etc, you get z prime equals this thing. So this gives you an expression for z prime, and you can integrate to find z. And this is pretty nice to do. So W is a Jordan chain vector, recall. Not recall, given that it's a generalized vector. So you find its Jordan chain because you know it's a generalized eigenvector, so that's very nice. Knowing that it's a generalized eigenvector, we can use the cool way to multiply it out. Except this is how you multiply etc times a vector w. In this case, we have e to the negative tc. This might bamboozle you a bit until you realize that you can actually just rewrite this as e brackets negative t c. And all this tells you is that every instance of t, you swap with negative t. And so our problems are resolved because you take this original form here and swap every t with negative t. Notice all of this works out, by the way, because that when we were dividing by etc, what we were actually doing is multiplying by the inverse matrix e to the negative tc. And this works out because when you take the inverse matrix, remember, you just take the negative of the power, which means you can just take negative t, and again, replace every instance of t with negative t. So there's no t here, and if there was a t squared here, it would be like a plus, and then a minus, and then a plus, and so on. And then you take e to the negative 5t up here. Okay, cool. We're in the home stretch because we have an expression for z prime, and we can integrate to get z, right? So note that for just the particular solution, which is what the question asked us, this term here will contribute to the homogeneous part. I'll show this in the expansion, but this part here is really the particular solution. So all you can do is just substitute c is equal to 0, right? You can substitute whatever constant you want technically because it's a particular solution, but really the particular solution part in this variation of methods part, method is this. And then you multiply it by etc because our solution was actually to get etc times z, our variation of parameter solution. That's what y is equal to. So this is our particular solution. So you might ask okay, then what's the general solution? The issue is we can't directly find the general solution because we don't know z, because we don't know the initial condition. So that's why the question was asking us for a particular solution. If we knew the initial condition, then we can directly substitute that y0, right, is equal to c, which is equal to this whole thing here. So we don't know it, but so we can just leave it in this form here. Notice that this is the homogeneous part from before, right? If we scroll all the way up, for the homogeneous differential equation, yeah, the calculation was just our xtc times the initial condition vector. We don't have that, so we can just leave that form here. Otherwise, we see that this is the particular solution. So if you were given a question which gave you the initial condition, make sure you expand this one out as well. And this would be your entire general solution. Cool. Yep. All right. And so to like sort of finish off this calculation where we have ETC and we want to find the particular solution, ignore this part here. So we want to like finish off and calculate the particular solution. We find ETC times each of these vectors. Notice that these are Jordan chain vectors, so we can use the method of calculating an exponential times a Jordan chain vector. This one here, there's only one term for the Jordan chain because this is an eigenvector, and for this vector here, it's a length 2 Jordan chain. So you introduce these two terms here, you expand out, and you get this as your particular solution. This is your homogeneous part. And so we're done. And this is how you solve ODEs. Homogeneous or linear ODE, multiple variable ODEs, homogeneous or inhomogeneous. Cool. Thank you for coming. Again, this was online, so I don't think this is applicable, but hope you all enjoyed. Yeah, I'll see if there's any questions in chat. Incredible. So true. Cool.